Hey everyone, today we are going to be learning about infinite series. So if you guys could go ahead and open up your Chromebooks to lesson 10.2.2, that way you can kind of follow along with these problems. All right, so what do we got going on today? It says, what is the total vertical distance a ball will travel if you toss it up and let it bounce? What if a bouncing ball continues to bounce forever? How far will it travel? Today we will discover ways to represent this situation and answer these questions. The first thing I need you guys to do is I need you to remember what we did yesterday because infinite series stem from what we learned from geometric series. So I need you to go ahead and remember or find, maybe look it up in your green notes, the geometric series formula. So as a reminder, that is the sum of all the terms. Let me get on a pen. The sum of all the terms is your rate as a decimal times your last term minus your first term. And remember, you need to multiply the rate times the last term first and then subtract that. So you might want to put some parentheses around this as well. And then you're going to divide that by the rate minus 1. Okay, so we're going to need to use that idea in these first couple problems. And this is where the infinite series stuff is going to stem from today. So we're going to do this bouncing ball problem. So what do we got going on? So it says, imagine lying on the ground and tossing a ball straight up 10 meters. When the ball gets back to you, how far has it traveled? Okay, so I want you to take a moment, pause this video, and try problems A through D. Why don't you guys maybe spend about 8 minutes doing this whole problem? All right, now that you've tried these in your teams, let's go back and see what's going on here. So question A, when the ball gets back to you, how far has the ball traveled? So it went up 10 meters and it went back down 10 meters. So in that toss, it went a total of 20 meters. B says, instead of catching it, imagine that you let it bounce. The ball has a bounce ratio of 60%. So you need to think back to math 1. I think that's where you did that stuff, the rebound ratio. So that means that each time it bounces, the ball will come back up 60% of its previous height. When the ball comes back down to you the second time, how far has it vertically traveled in total? So, of course, we have the 10 going up and the 10 going down to get that 20 that we already had. But we also need to go back up 60% of the way. So we're going to take 10 and multiply it by 0.6.
Please excuse this interruption. At this time, will all
Class
sophomores
meetings.
please report to the auditorium. Again, that's all sophomores. Please report to the auditorium.
All right, so 10 times that 60% of the way, that's 6. So we're going back up 6 this time and then back down 6. So if I add that all together, I have 20 plus the 12. That leaves me with 32 meters. Now we're going to imagine that we let the ball bounce 15 times. It asked us to write a geometric series to represent the total distance the ball travels until it comes back to you the 15th time. So remember, when we write a series, that means that we need plus signs and we need to include the first 3 values because we need to know whether it's multiplying or adding. So the first 2 values we already have. So that's 20 plus, we have our 12 plus. Now I'm going to need to figure out what that third one is. So if I take what I had previously, which is the 12, and multiply it by 0.6, I'm going to get 7.2. So that will be my third term because I'm doing this total amount every time. Plus, dot, 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 plus. And then to get the last one, I will have needed to do this a lot of times. So I'm just going to plug it into a geometric sequence equation. So we know that we started with 20. Our multiplier was 0.6. And then I have to the n minus 1 up here because I'm using the first term form. So our number is 15 minus 1, okay? And you can go type that out in your calculator, but I think you get some really small decimals, so I'm just going to leave it like this, but this is how you'd get it. Or you could use the zero term form. You could just put 15 up here, but then this would need to be the zero term, so you would need to go backwards. So instead of multiplying by 0.6, you would have needed to divide this by 0.6 and get a bigger number there. So it says, what is the total distance the ball will travel up and down? That's where we need to use that geometric series formula that I had you write down right at the beginning of this lesson. So to get the sum of the 15 terms, that's our rate, that's 0.6, times our last term. So with rounding, I'm just going to put this right in there. So 20 times 0.6, I'm just going to say that's the 14th. Because 0.6 times some rounded decimal, I may get something kind of off. So I'm just going to type it in like that, minus the first term. So our first term is that 20. And then I'm going to divide this all by the rate minus 1. So 0.6 minus 1. Do make sure you've practiced this in your calculator. A lot of times students just get it wrong because of that. So make sure, you do this first, subtract your first term, and then make sure this whole thing is divided by the 0.6 minus 1. We should get something like, it's approximately, but 49.9999999 or 98, I think, or something like that. So 49.98. So let's move on to the next problem here. All right, so now we're going to look at how far does it travel. So, of course, you know that a ball cannot bounce forever, but imagine that the ball can. So thinking about this possibility has led to some interesting discoveries. Will the total vertical distance the ball travels up and down continue to grow larger and larger? So now we're going to imagine moving according to the following sequence. So move 20 units, then 12, then 7.2, and we're going to keep multiplying the previous term by the 0.6. And we're going to continue to do this. This is where we're going to go to the handout. So if you don't have the handout, if you could go ahead and get that now. And I'm just going to scroll down here into the further guidance if you're following along on the ebook. And so 113 said you already calculated the total vertical distance for 15 bounces of the ball in problem 10-111. Calculate the total distance for 25 moves to the right for several larger values of n. Okay, so I have that formula rewritten there for you, where we have the sum of 15 on there for you, the one we already did. What you need to do is you're going to replace the n value with 25. So that's replacing, that 15 in the equation that you see. The 50, the 100, see what you get. Okay, so go ahead and do those in your calculator. All right, so we should be getting something like the sum of your 25 is 49.9998.6, and then the sum of 50, you get 49.999. You're getting a lot of lines here. And then the sum of 100, you might be using a calculator where it just goes ahead and says that it's 50. Interesting. All right. Looks like it's getting closer and closer to 50. Okay. So let's do problem 114 here. So it says calculate the sums of the following geometric sequences for n equals 10, n equals 30. On your handout, I also have you doing one more at n equals 50. So what I need you to do is, of course, I need you to practice using that formula, that S of n formula, the one that's boxed out on your handout. So using, okay, what's the rate? You need to figure out the rate for these. What's the last term? What's the first term? And then the rate minus 1 on the bottom. And then plugging the values in and then seeing what you get. Okay? So pause this video, I don't know, maybe 7-8 minutes or so, and see what you get when you do these things. All right, so for A, you should have gotten something like 399.609 and 399.9999, and then all of a sudden we're like getting so close, it's 400. And B, these numbers just keep getting larger and larger and larger. So I didn't even write all that down. They're just getting, they're just too big for me to write. So what's the difference between these? We have a multiplier. We have a B value that is between 0 and 1. And so when I have a B value that is between 0 and 1, my infinite series goes to a number. So it approaches a number. We saw that here with the bouncing ball. We saw that here with the half, right? We have a multiplier that's 0.6. That's between here. We have a multiplier of 1/2. That's between here. So when my multiplier is between 0 and 1, these numbers are going to get so small that the decimals don't matter. So when I add something like a 0.0000000000, it doesn't affect my number in the grand scheme of things, so I can approach your value. However, when my B value is greater than 1, then I get something that my number just keeps getting bigger and bigger and bigger and bigger and bigger. So the value is just going to approach infinity because the numbers keep getting larger, all right? So if we look at problem 115, it says using the situation in 10.1.12, that's that bouncing ball problem, what do you notice about the results for the total vertical distance traveled as you use larger values for n? That is, what happens to the sum as n increases? So what I have on your sheet of paper is I have 2 formulas. So what you see on the left side, that's the infinite series formula. So what there's 2 that you can work with. I'm not here, so I'm just going, I'd be happy to explain to you how it works. But there's some beautiful math that helps you get there. But what this actually sums down to is on the right-hand side. And that's that the sum of an infinite series is the first term divided by 1 minus the rate. And so if we explore that for the bouncy ball problem that we did, that the sum, let me go to a pen here. The sum of that, let's let the ball bounce forever, right? The first term we have, it's going up 10, down 10, so that was a total of 20, divided by 1 minus the rate, which is 0.6. So we get 20 divided by 0.4. And if you plug that into your calculator, that is an even 50. So when our rate is between 0 and 1, we get a value like this. And so I would definitely put this in your notes. Green notes, that second boxed one for the infinite series. So now we have a formula for an arithmetic series. We have one for a geometric series where we have like a finite number. For example, you would use that if you have, we know that there's 15 terms or something like that. You use this when you have infinitely many terms, okay? So get out your notes, definitely put this infinite series formula, add this to what we got. Okay, so you'll see your page jumps to 120. I'm just going to talk to you about problem 119, and then I'm going to have you try 120 in your groups. So Fanny is helping her younger brother Mac with his math homework when they come to this problem. Change the repeating decimal 0.63 repeating into a fraction. Fanny thinks, I bet I can write that as an infinite series, right? Because we have infinitely many digits, and use what we learned about geometric series to get the fraction. Okay, so it says write 0.63 repeating as an infinite series with a multiplier of 0.01. And so what we're going to do here is we have something like this. Oh, gotta go back to a pen. Let's write here. So I have 0.63, and we're going to use the multiplier of 0.01, and that's to the 0 power. And then we're going to add that to the next item. So I have 0.63 times 0.01 to the power of 1 plus 0.63 times 0.01 to the 2. And what's happening here, so obviously this is 1. I get that first part. I get that 0.63. When I have this 0.63 multiplied by the 0.01, imagine that decimal moving over 2, like that leaves these 2 spots for the zeros. And you can type this in your calculator to verify that. But that gives me the 0.0063 part. This is going to get me the now this is 4 zeros between here. So I have 0.000063. And this is going to go on forever because it's an infinite series. So what is the sum of the series? Well, we need to look at what the first term is. So the first term is what I see here. It's this 0.63. So 0.63. And then I'm going to divide it by 1 minus the rate. And that's 0.01. And I'm using that 0.01 because this repeats every 100th. So if it repeated every 1,000th or something, I would use 0.001. If it repeated every 10th, I could use 0.1. Okay, so maybe that will be a hint for number 120 and 121 when you work on those in your teams. So if I type this into my calculator, this simplifies to 7/11 as a fraction. So kind of interesting that any repeating decimal can actually be written as a fraction. So these are all rational numbers, which is kind of interesting because the decimals go on forever, but they can be written as fractions. So go ahead and pause this real quick and try 120 and 121 with your team. Say, I don't know, 8 minutes, maybe 4 minutes apiece to work on these, okay? Okay, so welcome back. So what do we have going on here? We have something like 0.143 this time times. Now, instead of doing 0.01, I'm going to do 0.001 to the 0 plus 0.143 times 0.001 to the first plus 0.143 times 0.001 to the second power plus ... because this is going to go on forever. And so I am going to put it in that infinite series form. So if I'm getting the sum of that, that is going to put me at, okay, my first term, 0.143 over 1 minus this rate, 0.001. And let me just go to my calculator real quick over here. I get 143 over 999. Okay. Ooh, this one was fun, wasn't it? So this is going to be 0.9 times 0.1 to the 0 plus 0.9 times 0.1 to the 1 plus 0.9 times 0.1 to the 2, etc. I'm going to come down here for this. So first term, 0.9 over 1 minus the rate 0.1. Ooh, so I get 0.9 over 0.9. What's that? 1. So you're telling me that 0.9 repeating equals 1? What a fun problem. Am I right? Okay, so what do we got going on for the rest of this? We have some practice problems underneath. So I'll just post, I guess, another video because this is like the lesson video. I'll post another one that has the solutions to that like walks through how to do each of those and what formula to use. So I hope you guys are having an awesome day. I hope I am too at the NCTM math conference in Seattle. I'm looking forward to seeing you guys when I come back. Have a good day.